So did you guys solve it? No? Any question? What? Well, it's also in mechanical solids as well, because it's very basic concepts. So it's, I would like to say that every mechanics course, basically it's a basic Hooke's law, right? So it's asking, we have so we have something like this. Assume this is our rectangular specimen, right? And we know this cross section, we have the dimensions. A, and this is under tension. T, and we are asked to find the strain, right? So let's use the basic Hooke's law, right? How we can calculate this strain? So basically, the stress over Young's modulus, right? So, in this, let's see if we have. Oh. I should have put Young's modulus here because. So Young's modulus. This one is equal to it should be obvious now. Sorry. Yeah, so if we have the Young's modulus, we just have to find the stress, and then this formula we can easily calculate this, right? And to find the stress, it's just force over the cross section, and we have both the force and the cross section. Is it clear? So any question about this one? Yeah, it's just a basic concept of this chapter. So if you don't have any question, let's move on to the next question. So this one is a little bit more challenging. Okay, so let's quickly just go over it. So it's similar to the previous question, it just have one more extras, right? So we are asked to find the elongation of this wire. So assuming we have I'll write it down here. So assuming we have a wire like this, it's again kind of like the same situation as the previous question. So we have a tension, but this time instead of strain, we are asked to find elongation. So the end is going to be something like this, and we are asked to find delta L, which is the elongation. So the first thing we can think of is, so if we have this strain, which is delta L or L naught, we can easily calculate this delta, right? So to answer this question, first we need to find the strain, like the previous question. And how do we find the strain? From the Hooke's law, right? So it's going to be stress over the Young's modulus, which kind of very similar, and we can replace the stress with force over the area, and we also given the Young's modulus. And let's see what we have here. So we have the diameter. So I write it down as R2 or D2 squared over E. So here we can write down our delta L as something like this, L naught F Young's modulus I and D naught. This is D naught. We basically just plug in all the numbers. We have all these information. So we have the initial length, initial diameter, and the force, and we are given the Young's modulus. And if you plug in all this information, that's the final answer here. Any questions? Yeah. So basically, these are the steps I follow. What? Yeah. So let's go back here. We have the numbers. So I wrote here. It's going to be 4 L naught F Young's modulus I and D naught squared. Oh, and one thing you have to be careful about in this chapter is just the conversion of the units. It's very important. So, what's our initial length? So it's basically 25 meter, right? It's 2.5 times 10 to the power 4 millimeter. And force is 500 Newton. And Young's modulus is 7 10 to the power of 9 and 5 multiplied by the diameter. Diameter is 3 millimeters, so be 3 times 10 to the minus 3 because we are converting everything to the side units, which is square. So let's move to the next question. So again, from the same concept, slightly different. Here we have a cylindrical rod, which is again under tension. And we are asked to find the diameter which satisfies that elongation. Time. Okay. So yeah, let's hold it together. Again, let's try to look up the equation. The main equation we have is the Hooke's law, right? Which is stress is equal to times modulus times modulus times strain, right? But let's break it down. So we are asked to find the diameter that satisfies this elongation. So stress we know is equal to force over area. But we are talking about diameters, which means we have to also break down the area to diameter, right? Which is pretty simple since it is cylindrical, so it's just area of the circle, pi times d over 2, again, square equals to Young's modulus times, again, we have to break down the strain as well because we are working with elongation. So we know this strain is equal to elongation of L over L naught, initial lengths, right? So it's more simple than that. We are asked to find the diameter that satisfies this equation if our delta L is equal to 0.5 millimeter. So if we just plug in the numbers and we have every other parameter, right? We are given the force we are given L naught, which is 380 parameter, the initial length, and also we are given the Young's modulus. So if we just move the parameters to find D, we get something like this. Modulus times output L, which is 0.512. So the rest is just plugging the numbers, and that's going to be the final answer. But again, be careful with units. Always try to convert everything to SI units. That's the safest way. And you don't have to memorize these formulas, just another version of that. So you always work with the main Fuchs law and just drive the formula for whatever parameters you are trying to solve for. Any questions? Okay, so okay with this. Let's move to the next question, which is a new topic of this chapter. It's again very similar, related to Book's law. It's basically the same thing, right? It's similar to previous questions, so just use Book's law to find the combination. So part B could be a little more tricky. So do you need more time, or should we go over the answer? So just think about it for 1 or 2 more minutes. Okay. So the part A, first part should be easy for you, right? Because we just saw like 2 or 3 problems similar to it. And I'm just gonna quickly show you. So basically the same with one. Stress, Young's modulus, and the string. And again, we're gonna break it down so we'll have a better idea. So stress is force over area, which is again, we have the circle. So most of the time we're going to see like circle, okay. So circle, which is like this, and we have the Young's modulus, and then elongation over initial x. And we are asked to find, for part A, we are asked to find this delta n, which is simple, right? Because we just plug in the numbers and we get delta.
Damn it.
So let's move to part B, which is asking calculate the change in diameter. So for the change in length, which is the elongation, we use the string, right? And it's kind of the same thing here, but we use a different string. So for the elongation, we use the string in the z direction. Or if we want to write it down more specifically, so this epsilon is like epsilon z, which is the same direction as the tension. But just show you like this. So if this is our cylinder and this is the direction of the tension, we take this direction as direction z, but right now we want to calculate the strain in the xy plane. So in other words, we want to find epsilon x, because epsilon x is basically
Yep.
delta d, or the change in the diameter, over d naught, or the initial diameter. It's the same as like delta d over d naught.
You said it was
So
Yeah.
how we
I
can
woke up,
find
it was 9:49.
this epsilon x?
Because honestly, even
So
from
we're
the
gonna
beginning,
use
I just made it
Poisson
look
ratio,
good, you
right?
know, I'm
Because
not
the Poisson
gonna make it
ratio
look good. I wouldn't have
connects
been this mad, I would have catch up on the other thing.
or
It was,
relates,
whatever he goes over the problem.
a strain in different directions, right?
If you want to. It was a hard one. I knew I might not do good.
This is like
This was
the
a
definition
I
of
was thinking
Poisson
emo,
ratio.
but then again,
Just
No,
epsilon
it's good. He's
x
gonna
over
that's why he has the
epsilon
problem.
c.
He's not gonna. Yeah, I already know.
And we know this number.
I already texted to him on Teams
Steven,
because I
right?
wanted to like try
Point
it out,
two
even if I
two.
don't get credit for it. So I'm gonna go to his office hours and get a paper and try it.
So basically, by calculating delta L, we are
No, like
finding the
cracks
epsilon
and
x
like
or
even
the
though like
strength
the gradient
use
point, like,
direction
if I could
part
still
A.
like see the particles.
And we're gonna
I
use
wanted to
that.
see what was on the place. That's all.
We're gonna use that
What do you mean?
epsilon,
that what
epsilon
you
z
asked?
plus this the Poisson ratio to find this
maybe after this,
epsilon
I can
x,
probably show
which
you
is equal to the change in the
at least the
diameter
problem. Besides two
over
impulse, from the
initial
it did
diameter.
similar.
And that's how we solve
Similar to
for
the.
It was still two
find
plus.
initial diameter.
Oh,
I'll just show you later.
okay.
Class.
Yes.
But you see the videos though, right? You
Does
see the
that make
videos, don't you?
sense?
Yes. I will still be watching that.
Clear?
I appreciate it.
Yeah, no problem.
Okay.
I will not be.
So I guess we have to move a little faster. So let's go to the next question. so let's think about it. Well, we need to find the original links or the initial links, right? So the first idea comes to mind is using the Hooke's law. So the Hooke's law, which is stress, Young's modulus, and the strain. But the problem here is we want to find the L0. Also, we are not given the force. So if we want to use this one, we have two unknowns, which is, so we cannot solve it this way. But it gives you the initial and the final diameters, right? So it's kind of similar to the previous question. You can find the strain in the x direction, the epsilon x, right? And how did we relate the epsilon? Well, it's kind of like reverse the previous question. This is the previous question. In that question, we had epsilon z, which is like the regular strain in the length direction, and also we had the Poisson's ratio, and we were interested to find the epsilon x. So it's kind of like opposite that situation. Here we have the final and initial diameters, meaning we can find that epsilon x. Let me write it down. So epsilon x is the, actually like delta d over d naught, right? If we had the Poisson's ratio, we could easily find epsilon z, and from epsilon z, we can find the initial links, right? So the key here is finding this Poisson's ratio. And if you remember from the lecture, well, we had, I guess, two different formulas for epsilon, for the Poisson ratio. One, which we saw in the previous question, is something like this. But also, we have another formula, which is this, right? This one. Or you might find this one in your after formula in your lecture in the class, but it's kind of like the same thing. To relating the Young's modulus and the Poisson ratio and the shear modulus, right? So, and you are given those the Young's modulus value and the shear modulus value. So here we can calculate the Poisson ratio, plus we are given enough information to find this epsilon x, which means here we can find epsilon z which is equal to delta L over L naught. And if we break it down, that is a final minus m naught over m naught. And we are looking for this m naught here. If you plug in all the numbers, I'm just going to write it down for you here. You will end up with a Poisson ratio of 0.322. And the rest, you just use this Poisson ratio and the epsilon x, find the epsilon z, and plug in L final in this formula, and your epsilon z to find L max. So yeah, the tricky part was using that formula to find the Poisson. Do you guys prefer we just go over and review the formulas, vector materials, at the beginning of each recitation, then go through the question? That would be better? Okay, so we can do that, yeah. Just review first. Okay. So, any questions about this one? Okay. Let's move to the next question. Let me show you this, because if you don't know the concept, it doesn't make sense to solve the problem. Okay, so resilience is basically the energy or the amount of energy absorbance in the elastic region, right? So if this is, for example, if this is our stress strain curve, one to the right, this part is the elastic region. And basically the area under the curve is showing the energy, which is the resilience. So the main formula is using an integral, right? This is like the area under the curve. But assuming we have a linear elastic region, so if we have a linear region, means, let's see if it has here. Yeah, basically can replace, so it's going to be like a, area of a triangle, because it's linear. So you can replace both of these. So if you replace like a strain with the linear relationship it has with the stress, you get something like this, and so resilience is gonna be that. Okay. Any question about resilience concept? So knowing that we solve this problem, so this should be easy now. BUR. Okay, did you get it? Yep. Yeah. So, yeah, we just like the modulus of resilience, which we showed with URs in the elastic. If we have linear elastic material, is equal to we can write it down like this. Right. So if we want to find like this yield strengths, just very simple, we can write it down. We'll change the formula to something like to this one. The same thing, just a simplification. And the rest is just plugging in the numbers. So we have 2 and saying the modulus resilience is at least 0.75 megapascal. So we can replace it with the lowest amount, which is 0.75, and doesn't have the Young's the Young's modulus in this question is 97 megapascal. So just be careful because one of them is megapascal and the other one is gigapascal. Okay, so let's move to the next concept, which is true stress and true strain. Are you familiar with true stress and strain? Let me see if I can find it before going through the questions. Okay, so let's review the concept first. So do you know what does like true stress, for example, represent? And what's the difference between true stress and engineering stress? So far, we use engineering stress. And we just in engineering stress, for example, we assuming we have something like a constant constant area or cross section, right? Because we always use the same cross section, but in reality, when you like pulling something, the length changes. Also, the cross section also changes, right? So the true stress is the real-time force divided by real-time cross-section. That's the concept behind like true stress and true strain. Why do we use engineering stress and strain? Because it's just easier to work with, right? We cannot like measure the cross-section and the lengths in real time, in real application. That's why we use the engineering stress. But in some applications, we also need to work with the true stress. And this is how the formulas are. Yeah, the true stress is the force, real-time force over AI, which is, I guess, real-time, yeah, instantaneous area or cross-sectional area. And the same thing for the true strain. So real-time lengths over initial lengths, but real-time the change in the length over initial lengths. And well, you have these two formulas which are very important. So that's how we connect like true stress and strain with engineering stress and strain. There is another formula, if I can find it here. Okay, yeah. So similar to Hooke's law, we have another relation, another equation which relates true stress to true strain. So it works the same way as the Hooke's law for the engineering parameters. So the K and N are constants. Good. And let me see. And the N parameter is called strain hardening exponent. That's also like the name of the N parameter. And the K is called, I don't know what it's called. It should be somewhere in the text. Okay. So now you got the idea. Let's move to the questions. Oh, this is also, let's just look at it. So it's the difference, like, if you have a tension test, for example, it's the difference between this true stress and the engineering stress. You see, the true stress is kind of like increasing always, because the cross section is just getting lower and lower and lower. But since we assume like constant cross section for in engineering stress, that's the curve we see like most of the times. Okay. So think about this question.
So we just saw the concept, and this was the formula, right? X like Hooke's law, but for true stress and strain. And well, in the first part, we are given the information for a tensile test. So we are given the true strain and the true stress plus the value of the K. So what we can do with those information, just plug it in this formula to find N, right? And we are given the K constant, and if we find N, then the rest of the question is simple, right? But how do we find N? So let's just, the math could be a little bit tricky because we are not working the linear relationship. But to make it linear, it's pretty simple. Always to make something exponential to linear relationship, it takes log, right? So if we take log from this equation, we'll have log, so sigma t is equal to log k plus n times log epsilon t, right? So now we can plug in the values we have for the test, for like the tensile test. Values. Let's see. So I have log 575 megapascal. It's equal to log K is 860 megapascal plus N, which we are looking for, times the log of epsilon, which is 0.2. 0.2. So from this equation, first we find N, and if you solve it, you will end up with a value of 0.25 for N. And again, we are given the true stress, right? And we have N, and we have K, so we just plug in N and K in this relation, plus the 600 megapascal, which is the value for true stress, and we find the strain. Well, actually, then you have to take another log because again, we want to find the strain is exponential, so you have to take log again. Is it clear? Or I can write down the second part as well, if that helps. So in this part we found N, right? And now we want to plug in all the numbers to find this epsilon t, right? What we can do is just, actually we don't need to take a log, because epsilon t to the power n, we use this one, is equal to k over sigma t. And just do this over m, which is Okay. Which is just quickly think about it, couple of minutes.
Mm.
So for this question over here, says log is equal to log k plus n times log epsilon t. So here you have two samples or two data points. You just can quickly, well, you can just plug in those data points, then you will have two equations and two unknowns, right? Yeah. So by plugging in these two and these in this equation, you will end up with two equations and two unknowns. Then you can find k and n. And if you have k and n, then it's simple, right? Because you have this string, you just have to plug in again this equation. Just have to plug in the true string, and we already found k and n to find the true stress. Okay, so also look at this question. Just think about it, just for 1 minute, just first part, have you calculated the stress? Because we have like a diagram, so, and we are asked to find the lengths. So it means we have to find the stress, then from the diagram find the strain, then relate it to the lengths, right? So in this question, well, you have the diameter and the force, which means you can find the stress. If you find the stress for the part A, you will end up with 136 megapascal. And just by looking at the diagram, is it elastic or plastic? An elastic region, plastic region. Exactly, yeah. So 136, somewhere around here, right? This is in the elastic region, which means if we remove the force, then we will have no, if the force is released, then there is no plastic deformation, which means there is no change in the length. So the final length is going to be the same as the initial length, 90 millimeter. For the second part, so the change is different. Then so we have to calculate the stress again. And for the second part, if we calculate the stress, we get 373 megapascal, right? So this one, we are in the plastic region. And somewhere around here, which is point A. So if you look at point A, you have 373 megapascal, which is the stress we calculated. And at that point, the strain is 0.08. But you have there's a slight difference here with the first part, which is like the hook style. Here, when you release the force, some of that change, which is because the elastic behavior of the material is actually back to the original, and you are you will end up with just the plastic deformation part, right? Let me show you. Yeah. For example, here in this curve. So here is the elastic part, but your stress is larger than the yield strength, which means you go through the plastic part. But when you release the force there, you don't end up with this part, but it's gonna retract a little bit, which is due to the plastic part, and you end up with this change, which is your plastic change. Is it clear? And that's the answer to your question. That's why we subtract a little bit, actually like the elastic portion of the total change. Yeah. So in our question, which is not this one, which is this. Okay, so this is our strain here. But we just said we have to subtract the elastic portion out of it. But here, the elastic portion is just so small, just 0.002. That's our elastic deformation, which is very small compared to this. This actually doesn't matter that much. I mean, you end up almost with the same answer if you subtract those. Doesn't matter here. But, well, yeah, assuming this is your strain, and just put it in this formula, delta L over L naught. Your L naught is 90 millimeter and your delta L would be 7.2 millimeter, which means your final length is 97.2. Okay. So the next part is about the hardness, but I think we don't have time to go through this one. So I'm just gonna show you on the textbook. So here, so we have different types of hardness, and you will see it in your homework as well. It's pretty simple, just based on the hardness. So you can have like Vickers, Rockwell, or Brinell hardness. You just use those formulas for the hardness. Yeah, and the questions are pretty simple. For example, here, this one. Well, here, yeah. Here is Brinell hardness, and again, you just plug in the numbers in those formulas. And this one is the Vickers hardness, and the safety factor, which is very simple. And you can just, well, yeah, this is the last question, the last section of this chapter. It's about the safety factor. The safety factor is just, for example, for safety factor of 2, the yielding strength is 250 megapascal here, right? When we are asked to consider a safety factor of 2, which means we have to divide that by 2. If it was 3, divide 250 by 3. Pretty simple. And yeah, it's something like this. It is like working is, that's the working stress. It's, yield strength over N, which is your safety factor. Okay. So any questions? Let us know if you have any questions from the homework, anywhere else.